I'm trying to share my screen.
I would like to add here that Hashem Shaika is a graduate of our program, and his paper that he's going to present today has been accepted in DG Twins for 2025 fall, and for the same presentation has received the Poster of the Year Award in National University 2024. Thank you, Hashem.
Hey, Dr. Sapara, thank you very much. Good to see you again. Hey guys, today I'm going to talk about digital twin representation of foliage, a study on creating a digital twin foliage representation through computer vision, image analysis techniques, and enhance the network planning and deployment. Before I get into my talk, a quick introduction about myself again. My name is Hashim, and recently graduated from in data science from National University. Professionally, my experience spans in AML applications, telecommunications, and cutting-edge wireless technologies. I have led AI-driven solutions in 5G technology integration and algorithmic optimization projects. Additionally, I have spearheaded cellular technology initiatives, including LTE and 5G. My expertise also extends to generative AI, building chatbot applications. Recently, I've been heavily working on those, playing with the multimodal data and trying to build a safe chatbot applications by integrating many frameworks or whatnot. What's going on? You all know about what's going on in this AML domain. Like Dr. Sapara said, we are working together in publishing my this topic in many forums as possible as we can, because this is one of the innovative concept, and there are many components or elements involved in it. And I'm trying to today talk about foliage as one of the key element which is going to impact this higher frequency technologies. Recently, the Digital Twin International Conference, they have accepted to present, and also I'm working with them to accept my paper also. And subsequently, I have a few more lined up to present, to submit my paper in various other forums. So how this research has been started, right? Why do we need to have this digital twin representation of foliage? Why now? I mean, was there any traditional or existing method to build this? Let's discuss all those things. As you see, right, in response to increasing demand for higher bandwidth, throughput, and reduced latency, that's where millimeter wave networks have become essential to the implementation of 5G. In today's rapidly advancing telecommunication landscape, the emergence of millimeter wave networks is a pivotal development aimed at fulfilling these demands to achieve greater bandwidth, enhance the throughput, and minimize the latency. But again, whenever there is a new technology, trying to provide all these kind of benefits, right? And then they come up with their own challenges. So basically, higher frequencies are more susceptible to the building structures and susceptible to the some of the elements in the environment like foliage and atmospheric absorption. Basically, if you compare with the older technology like LTE and third generation to second generation, the range of signal is much more than what we see in higher frequency technologies like millimeter wave, and they are more of line of sight, and anything that comes in between line of sight, like a building or foliage or tree, right? That kind of abstract and then absorb those signals and then cause signal degradation, and so that's what we are trying to come up with, a better way of how we can deploy these technologies if we know all this information ahead of time. So that's where this digital twin came into picture. So the traditional methods are like we do have traditional methods where similar information can be achieved. Where if you know about LiDAR, light detection ranging technology, where a small aircraft fly around the region and then try to collect all the information. With this approach, right, it's a pretty laborious and pretty and very very expensive. You need to have a pilot who knows how to fly the aircraft to collect that information. And at the same time, you need to have that device that can collect all this information. On the top of that, you need to have software because it's so much of information so that it can extract the required insights from those raw data. And not only that, every time there's an update, like, right, this environment keeps changing. Seasonal changes, like in summer you see like trees are full grown. In winter you don't see that many trees doesn't have leaves. And then the environment keeps changing. Basically, there are new buildings that come into picture. They might be removing those buildings, but every time you have this kind of change in the environment, you cannot have again the same flight flying around and collect the information. So what are the options that we have? That's where the digital twin comes into picture, where we were kind of like, hey, we need to build a digital representation of environment so that we get to know all these elements building information or foliage information, so that we can feed this information to the operators in their model, and then they can understand the suitable location by looking at all these elements. How can we build this digital twin other than the LiDAR information that we have? What is the much more sophisticated or efficient or cost effective solution? So this is where we kind of took some of the look at many options and look at hey, we have so much of aerial image, street view images, so we can see if we can get some insights. And then we have advanced so much in the AML domain. So we use some of the computer vision image analysis techniques to extract those objects of interest and try to build a digital representation of the element that we are interested in. So if you look at the right side, the image that we have. So this is how it's a digital twin is going to be, where I'm going to draw like some kind of a 3D representation of a block, from which in the simulation we can understand that, hey, there is a foliage. Maybe we can apply this much of attenuation, and then maybe the ray doesn't go through that. This is an indication that, okay, there is a obstruction, or there is a signal absorption that's going to happen at that particular point of time. And then we can also study like if there is a node placement in some point in any of these buildings or on the pole, and how far it can cover, how many points it can cover in the region. That way we can assess like whether this location, from this location, whether it is able to cover all the possible points, so that we can give a good user connectivity and good user data rates. So let's get more understanding on this. If you see on the diagram, right, on the right hand side, like I was mentioning about, there is a node here, and it's radiating, and that's why you see that this region entirely red, which is an indication of the region is very well covered. But if you see right behind those trees, the color is kind of yellow, which is the signal has been degraded. So, I mean, this is one example, but if you have the buildings, then the signal doesn't go beyond that. So looking at, if you have this information of buildings and foliage, see, we can plan saying that, hey, maybe the one node is not sufficient to cover this region. Maybe we need to place one more node so that we can cover this region very well. So that's what this digital twin model that is going to provide this information of foliage and the building information. And the operators, or the wireless communication operators, can use that model in understanding how many locations they need to place the nodes, so that they can get a good understanding of cost wise, and also like data coverage or data connectivity. Typically, in this whole process, the node is going to be placed on the either the buildings or street lights. So in my study, I chose street lights because we get that information through the municipalities. So we have that already known information of the street lights. The only thing is by having this digital twin model of with the foliage or building, we are going to identify suitable node placement on these street lights. So let's now we are clear that okay, we have the traditional way of collecting the information using LiDAR, which is a laborious and expensive process, and dynamic changes makes it much more difficult to keep collecting the information. So what are the other options? Maybe we have so much of aerial images, street view images. Maybe we can use our advancements in the computer vision image analysis techniques. We can use some of the object detection algorithms and build a digital representation of the environment so that that can be used by the operators in understanding the environment dynamics. So, like I said in the earlier, right, we said these higher frequencies have been impacted by this uh, uh, few important elements like a building structure, foliage, and atmospheric absorption. I didn't focus on building information because we already have that information. And recently, Microsoft has done similar kind of using some kind of through AML approach. They kind of shared billions of footprint of building information. But there's not much information. There was active research going on in the foliage, how we can extract the foliage information, how we can represent that information so that we can use that information also. So, and also there is an existing study done how foliage is impacting this higher frequency networks. If you see here, right, on the right side, it clearly shows that the vegetation loss depends upon the vegetation depth. So the various studies shows that the depth of the vegetation increases, the loss also increases. So it is important to consider in your network planning the existence of knowing the foliage and its details. Yeah, I mean, just to say that these are the existing sources that are available currently. Like collecting the information through LiDAR information or flying some drone. Other one is unnamed aerial vehicles. Like I was telling, right? It's the LiDAR is much more expensive because it involves a flight flying in the region, and there is an operator who has to fly it. He needs to have license. He needs to know how to fly that aircraft, and there is a software that is involved. So it's kind of like if you can clearly see that the cost wise it's a little bit expensive. And then we also have like some of the photogrammetric based drone services, and then we are comparing that with the aerial imagery. So out of all these options, we see that, okay, Google has been collecting. We also looked at the third-party sources of this imagery information. But looking at all the options, maybe we said, okay, Google has so much of information. They're collecting every now and then, every 3 months or 6 months, and they keep on updating that information. It's available, and there is a cost that involves every 1,000 images based on the API that you're using. They'll charge like $7 or $2. So it's pretty a very cost-effective solution. And then the only thing is you need to work on the AML algorithm that can get the insights, and then you need to apply your own mathematics behind to build that representation of 3D representation of the environment. So let's get into the how I'm doing that. Okay, so let's say that you want to deploy this technology in somewhere in the I chose Philadelphia downtown as one of the region, and then it's like I chose 12 square kilometer region, and once I know that, I kind of place the points along the streets so that I can collect. I need the satellite images as well as street view images. Let's focus on the satellite images so that from satellite images we need to identify the building footprint and then foliage information. And then how I'm going to train the model, how many points, again, the trees or foliage information that you see in the Philadelphia is different from if you go to the Australia. It's altogether different. So we come up with a model, we put it on the cloud, and then the operator comes up saying that, hey, I want to I want to deploy my technology in the so and so region. And then we go, the model goes there, collect all the satellite and street view images, prepares the model to fine tune those the trees or foliage information in that particular region, and tries to build the entire the model. In this whole process, like I said, I used aerial images and street view images, and I use some of the GIS tools, some of the Google APIs to build to collect all the information and to build this digital twin representation of foliage. On the right hand side, what you see is some of the satellite images that have been collected through the Google APIs, and we are going to use these images and feed this into the object detection model and try to extract, like I said, I'm going to focus on foliage, extract the foliage information. Yes, when you develop something, you need to know like whether the model or whatever you are building, you need to compare with some existing ground truth data. So what we did was we used some of the existing LiDAR data so that we can compare what model is outputting compared to the existing LiDAR information that has been collected, see how close these are. And I'm going to talk about whether it needs to be, how much close it needs to be. So we'll talk about that in subsequent slides. And for object detection, right? So the main thing is we need to do from those images, foliage information. The object detection algorithm is pretty crucial. And then after that, we use some of the Python open source library like OpenCV to extract the contours, and some of the GIS tools to build this, to map all this information back to the GIS coordinates to build this digital twin. And like I said, we started with YOLO, one of the popular object detection algorithm. And then we went with mask RCNN, and then we came back again YOLO. I'll tell you the story like why we started with the, when we started with the YOLO 5, there are some features that were not present. Then we realized that we need those features to be more accurate representation of foliage information. Then we went with the mask RCNN. And then when we are working with mask RCNN, YOLO has released version 8, which has come up with all those required features. Then we said, okay, let's move on with YOLO V8 so that we can process both street and aerial view images to get all those information. So this is simple flow chart that talks about how this entire thing is working. So like you have seen earlier in the presentation in the previous slides, we are going to collect a region of interest, and then we are going to and then there is like a we use some of the OSM or GIS tools to extract the street information, and then place the points at 30 meter apart. And then so we choose that 30 meter. There is some kind of reason behind how do we choose a distance between the points so that we don't do much of overlap when we collect the images, so that we don't double count the number of trees when we try to collect the information. So we don't want to duplicate so much of information. We want to get as much. We want to reduce as much overlap between those points when we collect satellite images. The one that you see on the right hand side, which is a little yellowish, is kind of street view images, which is open, and then it's still we need to do some more research on that front. On the right hand, on the left hand side, what you see is collecting the satellite images and then building the digital twin using that. That's what we already did, and then we kind of showed the results, and then I have some of the simulation results which we compared with ground truth data and see how close we are. I think I just talk about this one. So this is my source of information. So once we get the region of interest, I'm going to place the points with 30-meter apart so that we don't do much of overlap and collect all the information. I keep a street name for each point, and then X coordinate, Y coordinate, latitude, longitude. And angle is also important because I want to make sure that which direction I'm heading, whether I'm heading towards the north, south, when I'm collecting the information, so that I know that this street is heading towards which side. I mean, it will be useful in the subsequent calculations. So this is my source information from which I'm going to collect all the imagery information for both satellite images as well as street view images. So this is an example to showcase how I'm collecting. These are like some of the satellite images that I have collected. For 30-meter by 30-meter, you get these many pixels, 288 pixels by 288 pixels. This is collected at zoom level 20, which provides resolution approximately 0.1 meters per pixel. That's how it is 288 by 288 for 30-meter. So these are some of the samples that I have collected to build the digital twin. These are all satellite images that I have collected across those 1,000 points that I have placed. And I'm going to use this information, and I need to annotate to extract the objects of interest, and use the object detection algorithm to extract the insights, and then I'll explain the subsequent slides how this information is extracted and building the digital twin. So we use, like I said, we use one of the popular object detection algorithm, which is YOLO V8. And then we use both the open source VGG image annotator, which is one of the open source tool. And then I also use one of the commercial tool, RoboFlow, which is pretty good in annotating, which helps you like in the speeding up the annotation process. So if you see this, right, the top row shows the satellite images that I have collected, and then bottom row shows that how it has been annotated. Because I'm looking at only the foliage information, I want to train my model saying that, hey, this is how you need to identify the foliage information. I created a class called vegetation, and then the model has been trained. So I classified the entire data set into standard training and validation and test, and feed into my model, and then perform all this. If you see this red shaded region, that's where all the foliage information was there. So this was the validation results, and then prediction on validation. Just wanted to see how close we are in terms of what we have predicted, in terms of what we are the results from the model. And these are some of the standard metrics that I have followed to understand how the model is doing well. Intersection over unit is one of the key metric I use in my understanding how much overlap you want to keep. You want to give a threshold of to declare that it's a vegetation, a class of vegetation, the object that has been detected. And also I use it in my result analysis. I want to give some insight. So if you're familiar with this YOLO object detection algorithm, like I said, we started with the YOLO V5 and then moved to YOLO V8. In between, we started using mask-CNN. The reason was YOLO, when they started, whenever there is an object that has been detected, they draw a bounding box. So that's what it happens. But that was kind of giving us an overestimation of the area that has been occupied by the object of interest. So that was overshooting the estimations. So then we went to mask-CNN. Mask-CNN just masks the object area that has been detected, the exact area that has been occupied by the object. So that way it can be close representation of the object that you are talking about. And then these are like some of the precision recall curves in the whole process. We looked at both bounding box as well as mask, which came out pretty good. And some of the metrics, the precision and recall for both box and mask for the vegetation class that has been detected. So this is my results from the model. So when I feed all these satellite images, this is my model. What I do is next I convert this into a binary model, because a gray image kind of stuff. The reason is I want to eliminate all the other objects other than vegetation. I don't want to look at any other objects. So this helps me just to focus on vegetation, get the information of vegetation, and then point them back to the GIS coordinates so that we know exactly where this vegetation is present in the GIS coordinates. I'll explain this process, how it works. So we collected a satellite image, and then the model has identified the object, the foliage in that information. We converted into a kind of a gray. We eliminated all in the image. You don't see any cars, any other objects other than the area that has been occupied by the vegetation. Then we use OpenCV library. OpenCV is a library that we can use to draw the contours. And since when we are collecting this image, we know the GIS coordinates of this image. And then we calculated for all those contour coordinates, we calculated the GIS coordinates so that we can point back to the exact GIS coordinate locations. So this is what we did in locating the vegetation. So if you look at this one, in the entire region that I was dealing with, I was able to pinpoint the location of the vegetation. So I'm going to quickly go through. So this is one of the key metric I have used in terms of validating the results, intersection of overunion. So what we did was we have a ground truth data from the LiDAR. We have a data that has been detected by the model, and then see compare between LiDAR detected vegetation and versus what do you call model detected vegetation, and see how close they are. I mean, there is a process that has been followed where I split the entire region into a resolution of 1 meter by 1 meter, and then because I want to store that information, and then each box represents whether the vegetation is present or not in both the LiDAR as well as digital twin representation of foliage data. Then we can compare the data and see how much close they are. That's the approach that we followed. And we did this validation for multiple regions to make sure that how the results are comparable. So if you see the results, we compared across 7 subregions in the region that I have selected. We created 7 subregions, and then you can see that out of LiDAR detected vegetation, our model was able to detect 70%, 63%, sometimes 94%, sometimes 81%. And then we did like we went back and see why some of them are pretty high, some of them are pretty close. So there are some reasons, because the LiDAR data was a little bit old, and the Google aerial image we collected was maybe 6 months old. So this image will clarify that. Okay. So on the right hand side, what you see is yellow one is the foliage data from LiDAR, and then green is the foliage data from digital twin, and then the common foliage is a little bit grayed out, right? If you see this where my cursor is, this is the current satellite image from the Google, where there was no vegetation here, but LiDAR has that indication that there is a vegetation here, because LiDAR data was old. Maybe there was some existence of some tree that was present, which has been removed to make a way to into the building. So we have that kind of challenges with the old data. That's where I was telling that, hey, digital twin can accommodate this dynamic nature of changes, and then it's much more cost effective and efficient in planning your higher frequency network technologies. So that was one of the reason why there are some discrepancies in the matching up closer when compared to the LiDAR data versus the digital twin data. Okay, so when we collect the information from the Google or any third party, there are some kind of we need to pay some attention, because we need to make sure that we are not mix and match of seasonal data. So you're not collecting some information from the summer, some information from the winter, so that so you need to make sure that you get the information from the same season, so that the tree is full grown or whatnot, right? So you need to pay such kind of attention. Okay. So I kind of you can see on the right hand side, I collected some satellite images across different timestamp. So we need to make sure that the satellite images. Sometimes Google doesn't advertise all these things. They look at they themselves have some kind of quality check. So if you see here, right, there's no way I can get any information because there are clouds that has been occupied, and then there's nothing I can get. And sometimes if you see this information, they are not true orthogonal. That means they have been tilted. So sometimes when you have this, it doesn't have true orthogonal. That means when the building is tilted, you don't, if it is a tall building, you don't see the foliage underneath. So you need to make sure that the data collected is a true orthogonal, or is it a oblique. So we need to make sure that if you know the information of the angle, maybe you can correct that information to some extent. And it's clear from the clouds or any other shadows. Make sure that you collect all data from the same seasonal so that you don't deal with mix and match. And also, like I kind of submitted some kind of a request to Google satellite and Street View APIs to provide some kind of option to collect the data from a specified period. I think that's something that Google is not releasing that information. Maybe I don't know what exactly, but there's a lot of requests from many folks to have that option. Maybe they will release so that we have much more control.
And Hashim, we just have about 4 minutes until the next presentation.
So I think you got pretty much what it is. I'm going to quickly jump onto a simulation. What you see on the screen, leftmost is where the like I was mentioning, like Philadelphia region that I have selected. I'm going to collect all the satellite images in the red polygon, and then try to get foliage information for that region. And also from the municipality, I'm going to get street light information, the pole information, so that I can place the poles in the location. And with the availability of building information and foliage information, the model can assess out of all these 1,000 poles that I see in the region, what are the best options for me to serve the entire region. So that's what its simulation shows. Maybe in a few minutes, you'll see that some of the poles gets populated with a different color, showcasing that these are the out of those 1,000 poles, maybe like there are like 40 poles that have been selected to serve better in this region. Yeah, so right now I place the foliage, which is a polygon representation. You can also see that how closely it is matching up with foliage that is already present from the Google Earth. So give me a minute. Yeah, you can see that red dots that indicates these are the poles that have been selected based on the existence of foliage information, building information. Hey, if you have the node, the technology node placed in these locations, this can serve this entire region efficiently with good user connectivity and good data rates. On the right hand side, what you see is like I was mentioning that I was playing with a lot of GIS tools, the 3D representation of the building information, and the 2D maps in both in QGIS, one of the GIS tool representing 2D and 3D version of the map. I want to show you the results. So this is what you see on the left hand side. When I place my the model outcome, you can see that how it is it's kind of overlaying on the top of the existing foliage. And this is how the model predicts the foliage presence, not only the foliage, but also building information. And then this information get into the in the wireless operator simulation, and then they can say that, hey, there's a block here, it's going to attenuate and it's going to obstruct the signal, so it's not going to cover any points that you place behind those. So this is how they can come up with innovative solutions. And also, like I was mentioning, that they can also play with if there is already existing technology that has already deployed in these locations. They can also see that hey, maybe there's already existing technology. Maybe we don't need to place at the same location. Maybe we can move on to some other location because the existing technology can cover this region. And also, like recently, I come across that if there is a fixed wireless network, basically there are some fiber routes placed. So we can also consider that and then place a node such that it's close to the fiber access point.
Thank you.
Way that
and we're right at time.
Yeah.
So if anyone has questions for Hashim, I hope that they can reach out to them, or possibly Hashim can answer that on Zoom. But I'm going to turn it over to Dr. Sapara now.
Thank you very much.
Thank you, Dr. Shaikh, and we can move